to the notes for parallel and coincident lines. I've already put on the website a Desmos illustration or demonstration on the concept of solving simultaneous linear equations and the fact that we don't always get a unique solution. We may in fact have no solutions for parallel lines or an infinite set of solutions for coincident lines. So a couple of examples to look at here. You saw in the demonstration that for parallel lines we're looking at having the same gradient but different y-intercepts. And I'll give you an example here where x and y are both on one side of the equation. So it's not in the form of y equals mx plus c at this particular stage, so it may be a little bit difficult to spot what the gradient is and what the corresponding y-intercept is for each equation. So if we take these two equations here, and I've labelled them equation 1 and equation 2, and we manipulate each equation to isolate y, and on the CAS calculator you could actually do a solve for y and actually rearrange this on the CAS to be y equals. And once we perform these operations here, we end up with equation 1 becoming y equals negative a half x plus a half. Now I've relabelled that as 1 dash because it really is the same as equation 1, just in a rearranged form. So when you're trying to keep track of your equations with simultaneous equations, have a nice labelling system such as this where you know where each equation is derived from. The second equation you can see here, equation 2, is of this form originally. We have to rearrange it to be y equals mx plus c, and I've called that 2 dash. Now when these equations are in this particular form here, we can see the gradient of both lines is negative a half. So that's the first bit of information that tells us we may have parallel lines. But we now need to check that we have different y-intercepts, because in this case over here, the same y-intercept would give us coincident lines. So rearranging this, we have a half as a y-intercept of equation 1 and 3/4 a different y-intercept for equation 2. So not overly interested in these values, interested in the fact that they are two different y-intercepts, and therefore we would have parallel lines. Now if we have parallel lines, as we saw before with the demonstration, those lines will never meet, they'll be parallel, and we'll get no solution. If we did try and solve these equations simultaneously, and you can take these two and maybe do elimination or substitution via these two equations, you'll get equation 1 equal to equation 2, and you'll see the minus half x on each side will cancel out, and you'll end up with a statement that says a half equals to 3/4. Now that's a nonsense statement, that can't possibly be true, so we know we have no solution caused by parallel lines. Moving on to a very similar example, and you'll see all I've done is change the value there of the second equation from a 3 to a 2, so the algebra becomes very, very similar here. So equation 1 is rearranged as we saw before to be negative a half x plus a half, now called 1 dash. And equation 2, I haven't done all the steps here, but you can see what used to be 3/4 as a y-intercept. I've changed the 3 to a 2, so we've got a new y-intercept of 2/4 or a half. So we actually have the same equation. Equation 1 is exactly the same as equation 2. And you can see in this form here, x plus 2y equals 1. If I double all the terms, x becomes 2x, 2y becomes 4y, and 1 becomes 2. So in fact equation 2 is just two lots of equation 1 in that situation. Again, if we didn't spot it at this particular stage, we try to solve simultaneously. This sets up very nicely for elimination, so everything's subtracted from the top line here. Y minus y is 0 on the left hand side. That term, subtract that term, is also 0, and a half minus 2/4 would also be 0. So we'll end up with a very obvious statement that 0 equals to 0. Now unlike this nonsense statement here, which couldn't possibly be true, this situation is obvious and always true. Now when it's always true, it doesn't mean that all values of x and y will be solutions. It means that we will always be true for points or values of x and y which lie on the line. Which line? Well, they're both exactly the same line. So if you can give me a value for x and y that satisfy either of those equations, you'll have a solution, and in fact there'll be an infinite amount of solutions because those lines are one and the same and they are coincident. Fundamentally that is a nice way to approach these particular questions, to rearrange in terms of y equals mx plus c, and you can very clearly see what the gradient is and what the y-intercept is, and make a decision based on these two extreme cases, whether you have no solutions or an infinite set of solutions. I will encourage you to start using matrices, and some of you that didn't come through the advanced general course may be a little bit hazy with the work on matrices. You don't need to know a lot to actually perform this particular part of the course, but what you will need to know is basically how simultaneous equations are solved using matrices. I've changed colour code here, so the coefficients of x and y are labelled in red, x and y are labelled in blue, And our constants, I've just called them M and N. In this particular case here, they were 1 and 2, and 1 and 3 over here. They could be any particular values. I've chosen M, and now M is not to be confused with the gradient. M is just a particular value that you could choose. Quite often you're going to see the use of M in these particular equations, and it's not going to be the gradient. It's just going to be an extra variable that's put in to ask you to rearrange the equation. So in this particular form here, two equations, if we wanted to set them up in matrices, you'd see capital A being a 2 by 2 matrix which has the coefficients. So A becomes 1, 2, 2, 4 based on those coefficients. You must get these in the correct order. X plus Y equals a constant. Our X term is what we'd like to solve. We're always solving for X. And X becomes not just the value of little x, but X and Y in a matrix. On the right hand side we have M and N. And again, this is going to be a matrix M, N. The operation to actually solve this particular matrix, if we set it up as AX equals to B, and if we were to rearrange and fully solve with the matrices, we'd find that X equals the inverse of A times matrix B. Now we don't have to use the whole matrix operation to solve it, because what we're looking at is the determinant of A. Now the determinant of A is used in the process to find the inverse of A, and we don't need to go through the whole process. We do need to identify what the determinant is going to be, because it will give us some clue as to what sort of set of solutions we might have. So very quickly with the work here, with these you're labelling these A, B, C and D. These are just positions in the matrix. So as we work across A, B, C, D, and our formula for the determinant of A, which will be used in finding inverse of A, is AD minus BC. So it's a straight operation to multiply 1 by 4, they're the positions of A and D, and subtract the corresponding diagonal of 2 by 2, which is BC. When we do this, we'll end up with 4 minus 4, which equals to 0. Now we don't have to go any further, because in actual fact we wouldn't get a unique solution, but that is identified that we either have the case of parallel lines and coincident lines. So for summarising here, if you find that determinant of A equals to 0, then you have this particular information. We know that we do not have a unique solution. If we do not have a unique solution, we must have one of these two extreme cases. And you can go ahead and work out which of those cases it is, and we'll be doing that with the examples in class. Having a quick look at this, however, if you did identify that you didn't have a unique solution, then it's really a case of saying, well, are the two equations going to be exactly the same? Is one equation a multiple of the other equation? Or do we have this situation where we get no solutions because one equation on the left looks like a multiple, but on the right is not a multiple? So again, that'll be work we'll further explore in the class examples, but this will give you the basics in terms of the different cases, the algebraic manipulation to get it into the form of y equals mx plus c, so we can compare, and some brief introductory work on the matrices, which is the preferred approach to actually identify what sort of set of solutions we might be looking for in the question. So that's all. As I said, we'll pick up the questions and exam style questions in class for next year. Thank you.